Okay, let's talk about domain of functions. So if a function f does not model data or verbal conditions, its domain is the largest set of real numbers. This is the symbol for all real numbers, okay? For which the value f of x is a real number. So if the problem doesn't tell us what the domain is, then we're automatically just going to assume all real numbers. But we have to exclude from that set of real numbers a function's domain. Exclude from the function's domain real numbers that cause division by zero and real numbers that result in an even root, such as a square root of a negative number. Okay, so we can't have a zero in the denominator and we can't have a negative under an even root. Those are our two restrictions. So simple terms. This is how to find domain. If it's a polynomial, it's going to be all real numbers. Always. No exception. If it is simply a polynomial, any number between negative infinity and positive infinity will be true in that statement. Okay? That's why it's all real numbers. That's why. Now, if it's rational or fraction, right? Rational means fraction. Oh, here we go. Buckle in. It's going to be a fun time today. Fraction. Rational, fraction. That's what that means, the same thing. So, if it's a fraction, we're going to take the denominator, set it not equal to 0, and then solve, okay? I should have said and solve for both of these. And if it's an even root, like square root, fourth root, sixth root, anything even, then we're going to take the radicand, set it greater than or equal to 0, and solve. Now the radicand, in case you don't know what a radicand is anything underneath the root, okay? Like underneath the square root, it's the whatever sits underneath the root. So let's look at these examples. So we have f of x equals x squared minus 7x. This is a polynomial, okay? We have x squared minus 7x. We start with the squared, we go to the x to the first power, and then, well, plus 0, so that would be a polynomial. So we know that this guy is a poly. And what did I say up here? A poly is always all real numbers, right? So for the domain on that, we all know domain is always denoted by a capital D. So it's going to equal negative infinity to positive infinity. Cool. Without fail, this is always going to be the domain. Right on. Let's go to another one. Now, let's look at this one. Well, it's a fraction. So, oh, I thought I would have swore I changed colors. All right, so it's a fraction. It's called rational. So either one you want to put. I'm going to put rational because that's the mathy name. We know if it's rational, then we set the denominator. I'm going to spell that all the way out. No, I'm not. Denom not equal to 0 and solve. Okay, denominator, what's on bottom, right? We know that. So we're going to take x squared minus 2x minus 3, set that not equal to 0, and solve. In case you don't know, an equal sign with a line through it means not equal to 0, okay? It's mathy terms. All right, so let's talk about this polynomial. We know it's going to be the factors of 3. This sign right here tells us it's going to be opposite signs that subtract to give us negative 2. This sign tells us that the bigger number gets the negative. If we look here, we have x squared. Turn that around. That tells us there's going to be 2 x's. So now this is pretty easy peasy to figure out, right? So if we know all that facts, 2 x's. Factors of 3. 3 is prime. We know that's 3 and 1. it's different and the bigger one gets the negative, well, that's got to be -3, +1, right? Pretty easy, right? Okay. If you don't know that trick about the signs, send me an email. We will like Zoom or we will talk, and I'll turn you on to that little bit of information, and it is a game changer. Okay, so now we're going to set x -3 cannot equal 0, x +1 cannot equal 0. So we're just going to move this over. So that's going to be x cannot equal +3, x cannot equal -1. Now, my favorite thing to do now is to put this bad boy on a number line, because we know that we've already assumed all real numbers, right? So from -infinity to +infinity is all our real numbers, but it can't be these two. So surely we know -1 goes on that side and 3 goes on this side. If you don't, again, send me an email. Now, anything here is game. Anything here is game. Anything here is game. Cannot be -1 and it cannot be 3. Okay, so let's do this in interval notation. Let's go back to the pink color. So we always read left to right. So we're going to start at, -infinity. We're going to go to -1. We have to make a jump here. So remember, any jumps we're going to denote with the horseshoe looking thing, which is a union. Now we could jump but pick up right here. So again, -1 all the way to 3. It's fair game, but we have to jump 3, and then we pick back up on the other side of 3, and we go to positive infinity. So this is our domain for this guy. Okay, hold on. Let's go to the next one, which is our h of x, and we'll do him in orange. So he is an even function, or I mean an even root, sorry, getting way ahead. With an even root, we set the radicand greater than or equal to 0. So and then solve. So what would our radicand be? What's under the root, right? So it's going to be 3x plus 12 greater than or equal to 0. Okay, now let's move the guy who stands alone. So it's plus 12. We're going to subtract 12. What you do to one side, you have to do to the other, right? This cancels. So we're going to have 3x is greater than, oh my, sorry guys, I did whatever it was, I did it again. Sheesh. Is greater than or equal to -12. So I'm going to go up here so I have some more room. So 3x greater than equal to -12. Divide both sides by 3. So x is greater than or equal to -4. My goodness, 4. Okay, so now let's put him on the number line. So this is a really cool trick. If you have your, it's an inequality and you have your x on the left hand side, you could always use your inequality like an arrow, right? So you know your x's are going to be going in that direction. So it's going to be going this way. So, but it's a greater than or equal to, so we know that this is going to be bracket -4 to infinity, right? And this is our domain. Very good. Now this one's kind of tricky. I put it in here not to be tricky, just so in case you run into anything like it, you would know. It's 2 in 1, actually. There's 2 rules involved in this one. All right, so we have 2 rules. It's irrational, but it also has an even root in the bottom. So first we have the even root. That is not the way that should look. Man, I think it's tired. And then 2. Oh my gosh, I'm so sorry, you guys. Is the fraction. Okay, man, maybe I should just say it and you guys should just write it down. Okay, so the first thing that we're going to do, normally with an even root, we set it greater than. And here we go. Good times. We set it greater than or equal to 0, right? But because it's a fraction, it cannot equal 0, right? So we can't do greater than or equal to, so we're simply going to take the radicand and set it greater than because it's the 2 rules. So we're going to take the 14 minus 2x and set it greater than 0. Only because of the 2 rules though, right? That's why. So now we're just going to solve it like we normally would. We're going to subtract 14 from both sides. So it's going to leave us a negative 2x is greater than negative 14. I have to switch colors because we're not going to have much room here. So if we divide both sides by negative 2, it's an inequality and we divide by negative 2, we have to flip the inequality symbol. So these are going to cancel. And that's going to leave me with x now is less than 7. Okay, we could put that on our handy dandy number line. If we have 7 and x is less than him, our domain, oh my, is going to equal negative infinity to 7, and both of these are going to be parentheses. Okay, sorry, that was really crowded. Okay, but that's it for those, and that's all of the examples that I can possibly think of for you to have any trouble with domains. Okay, all right, let's do that. No, what just happened? Don't know. There we go. And now let's go down a page. And maybe another page. There we go. So this talks about when to factor and when not to factor. On the first one, we did not factor because it was just simply a polynomial, right? It wasn't in a denominator. So when it's a polynomial, we know that it's all real numbers. or negative infinity to positive infinity. Now, on the other hand, the example 2, we had to factor because of the restrictions, and it was in the denominator. So that's when to factor and when not to factor, right? If it's just a polynomial by itself, it's not in the denominator. Don't worry about factoring. Just be like, oh yeah, that's a polynomial, negative infinity to positive infinity, and roll on, okay? Don't spend a whole lot of time on it. Okay, awesome. I'm going to exit that drawing, and I'm going to scoot up some so we could talk about some algebra functions. No, I'm going to end this one and do algebra functions, so y'all have a different video, because that one was 15 minutes long. You're welcome. Okay, have a great day.